So the motivation for physicists to do really, build quantum computers is essentially the point of view that a universal quantum computer is a perfect quantum simulator, which basically means that I can simulate anything I desire, any physical phenomena, which is a quantum mechanical phenomena. I should be able to. Okay, so in recent times, we have seen this work, very interesting work coming up, where non-abelian braiding of graph vortices in a superconducting processor. This is published by Google collaboration. And this essentially uses something called stabilizer codes, a sophisticated version of stabilizer codes. And this is something I'm going to kind of introduce to you very briefly during my talk. So it's not a story, it's becoming a reality that we are really able to use it, these quantum computers to do fancy physics. So what are the most recent platforms on which we are trying to build quantum hardware? Some of the platforms which you already heard in this conference: superconducting loops, then you have trapped ions, then you have silicon quantum dots, then you also have topological qubits hoping to be built on quantum Hall platforms, then you have NV centers, then you have neutral atoms, then you have, of course, the photons. So all these are competing platforms which are being considered and pursued. And you can see that, of course, all of them suffer from errors. And the error rates as a function of time seems to going down. Is going down differently for different platforms, but it seems to be going down. And this is what IBM is trying to build. You can see that we are now at intermediate scales. So at some point, these numbers, I don't know why they have such bad resolution. This was 2019. They had 27 qubits, and they are hoping by 2022 and 2023 and I can't read this number. So I think it's in 4 digits. That's what it is. So it seems to be going pretty well. And hoping that we'll have a reasonably large quantum computer. But I think the question would be that as the system size becomes larger, does this thing also goes down? If it doesn't go down, it is useless. So now quantum computation. So what are the ways in which we can do quantum computation? Of course, we can use classical platforms to simulate quantum to run quantum algorithms. This is one possibility. This is an expensive possibility, and many companies are doing that. Then you also have quantum annulars, which D-wave systems are doing. Then you have the intermediate scale noisy quantum computers, and this is particularly what we are going to focus on. So what is the idea? So one of the popular idea for implementing quantum computation is quantum circuits. So this is a gate-based strategy where you essentially have, it's pretty much like a classical computer. You have input channels, you have n number of input channels through which you can input qubit information into each of these channels. And then once you have done that, then it goes through some unitary operations, which are called quantum gates. And finally you measure, and that's your outcome. So essentially you have some bit string which you put in. You can think of it as a bit string, this ups and downs of this qubits. And what comes out on the other side is also some ups and downs. And in between, what happens is what you will call the computation. And now the errors can come in at 3 levels. Of course, it can come in when you try to reset this or essentially initialize all these qubits. Error can also creep in as you use the unitary quantum gates. They can also creep in as you do measurements. And we would like to essentially, so there are 2 steps. One thing is we would like to understand the character of the error, and then we would like to correct it. Now, my motivation here is to tell you that it's possible to, so it's error correction is of course a procedure which definitely need for building large quantum computers, but reliable quantum computers. But before that, we really have to understand how to suppress noise or errors. And for that, we have to understand what the errors are. So it's not enough that you really correct them. You have to really understand them. So that is why I'm saying that what I'm going to show you is not quantum error correction, but quantum error detection. It's going to detect exactly where the error is happening. So imagine that through this channel a qubit is passing and it appears here and you get some information. Looking at that information, you would like to conclude really the error happened exactly where in this channel, or this channel, and what is the character of the error? Is it a bit flip error? Is it a phase error? What kind of error is it? So you want to do an error detection, not a error correction. The central theme of our work, it's essentially that is entanglement a resource for error detection? This is the question we are trying to answer. So let's first try to understand if if entanglement is a resource at all. So let me start, it's just for warm up. So let's start with the Bale state. So if you look at the Bale state, it looks like this, where you have the first qubit prepared at 0 times the second qubit prepared at 0, and then you have plus the first qubit prepared as 1 state and the second qubit prepared at 1 state, and this is in the Z basis. This is one of the possible Bale state which you could take. And then the important point to note here is that if I want to look at the reduced density matrix of this state, so if I trace out either the subsystem A or the subsystem B, what I get is an identity matrix, half-time identity matrix. What does it tell me? It essentially tells me there is no local information on the first or the second qubit. So it's telling me that all correlations, all informations are essentially non-local. There is no local information. This is what it's telling me. So now how can you use it? So one possible use is the following, that you ask somebody to prepare a bunch of qubits, let's say n of them, where n is large, and send one to Alice and one to Bob, and leave it there, and then you fix a measurement protocol such that Alice makes a Z measurement on these qubits, following which Bob makes a Z measurement on these qubits, and essentially it generates a bit string. So essentially what you get after the measurement, the Alice essentially gets a bit string, and of course Bob also gets a bit string. And because of the character of the state, you can see here it's an entangled state. So if Alice generates a bit string, exactly the same bit string will be generated by Bob. So the interesting point is that once I do this operation, I do generate a bit string. It's completely random, and that's what I call key. And what my intention is that I will have an information, binary information, which I would like to secretly send using this key. So how do I do that? So what entanglement is allowing me to do is essentially pass on a random number from here to there without anybody interrupting in between, right? I'm non-locally sending off a complete random number. It's complete random because it has a 50-50 probability. Every measurement is 50% probability of having up and 50% probability of having down. So if n is large, it's a completely random string, and it can be converted into a random number. So essentially, I have a random number which is on this side, which Alice measures, and because of this measurement, exact copy of that is being transported here. So that looks fantastic. So what do you do with it? So you have now the key and the binary information you want to send, and what you want to do, you essentially want to add your information, what you call information, which is a bit string of the same length. You add it to the bit string which is generated by this measurement, and this sum is something you classically send just over a phone call. Once you send it to Bob, what Bob does is a binary operation. It adds k plus I, but if you have two binary operations, if you add them, imagine that both are 1 and 1, so 1 plus 1 is 2, but it's a binary operation, it's a binary addition that will be reset to 0, right? If you add 0 plus 0, that's also 0. So essentially, this is like adding nothing. So k plus k is adding nothing, so essentially you get back the information. So if somebody even interrupts this information, it will look totally random because you took something which is very random, added your information on top of it. So essentially to that person, no information will be extractable, right? So that seems fantastic. And you could do this. So basically, how do you know you are really doing fine? Nobody's interrupting. So basically, you can perform a Bale test on it because it's a Bale state. It should give you, it should kind of conform to this inequality, which is 2 root 2. So if it doesn't confirm, you know somebody is interrupting. If it's confirmed, then you know that everything is going fine, right? So we had two quantum advantages here. So we do not know, in principle, if there was no quantum mechanics, we really do not know how to perfectly generate a perfect random number, right? So in the first case, what we are saying is that quantum mechanics allows for generation of a perfect random number. That's one usefulness and an advantage. The second advantage is that the entanglement allows to convey this across spatially distant partners instantaneously without even knowing what the random number is. So I could pass on the random number, which I call the key, and I don't even need to know what that random number is, right? So this seems fantastic, and so this is what comes out of entanglement. Seems like it is a useful thing, and this is one possible use of it. So now, what is it that comes out of this math which we are doing here, the partial trace? This identity seems to be a very important thing. The identity is telling you that you have no information. Seems like no information is a very powerful thing. Usually we say it the other way around. Here, identity seems to be a very important fact, that it is identity. Now, we can theoretically ask this question, that of course for the Bale state it happens, can I generalize this concept for a higher number of spins? That's the question we'll try to ask. And then, of course, you can ask the second question, which is the theoretical question which you can ask, a mathematical question, an experimental question, that can you have for those states an analog of Bell's inequality so that you can do checks, right? So the question boils down to this. So what we are looking for, what are you looking for? We are looking for a given collection. So what you are asking is for a given collection of n qubits, capital N qubits, spin halves, can we write down a state such that when we trace out any n qubits, small n qubits, any, I'm using this thing any, it's important, right? Then we get an identity matrix in the reduced density operator, right? So can you write down a state which is such that it's an n qubit, capital N qubit state, I take any 5, 10, 25 of them and trace it out, any of them, I'm going to get an identity matrix. If I can get that, it is analogous to what we had for the Bale state. It's very similar. It's telling you there is some lack of information within that subsystem. And you can choose any of those subsystems. It lacks information, right? The information is non-locally spread over those patches, right? So that's what it's telling you. And so alternatively, you can say it has an entropy, maximum entropy allowed for the subsystem, which is n times log 2. Right? So is this useful? How can you use it? And that's the question we are trying to ask. And I will show you that this is very useful for error not correction, but error detection. So what is a useful mathematical tool for it? So you have the generalized block basis, which is very simple. So for a single qubit, you have the identity matrix and the 3 Pauli matrix. So essentially for n spins, you can just take a direct product of this basis and that will generate a basis for you, right? For n spins. So that's what is the block basis. And now let's do something. Let's take the Bale state, which we just studied, and write the density matrix in this basis. If you write it, what you observe is that it is 1/4 times identity cross identity plus x cross x plus y cross y plus z minus z cross z. What is it that you observe? You observe that this state, I'm a physicist, so the first thing I will say is that I observe that if this was physical spin, the state is such which has 0 magnetization, right? That's what we observe. But what implications does it have? It has interesting implications that because those terms are, so essentially every operator which appears here, the coefficient is the expectation value of that operator in that state, right? So it's telling you there is the expectation value for magnetization of either the first or the second spin. But that's the physicist way of looking at it. You can even ask questions about does it have anything to do with time reversal symmetry and so on? Is it necessary that if you have time reversal symmetry and if you take the subspace which has time reversal symmetry, it will necessarily have this property? That's an interesting question. I will not answer it now, but this is the state, those correlations, those expectation values are vanishing here. And just looking at the density matrix, you could tell that if I take a partial trace, I'm going to get identity. So having the identity and having the absence of those terms or the expectation value for those terms is an equivalent thing, right? That's what it is telling you, that those things are absent. So now you can start extending this. So I'll give you so you can start extending this. It turns out that these graph states, so I will tell you what a graph state is. A subclass of graph states actually fits the bill. So now let's see what is a graph state. So I'll tell you what a graph state is. So essentially here, this is what I take is a simple undirected, unweighted, and without multiple edges or loops. This is the kind of graph I take, and I claim that there's a one-to-one map to a pure n qubit state, and the mapping goes like this. So if you have the density matrix for the graph, if you want to write down the density matrix for this graph here, what you do is you look at this node, you think of each node as a spin sitting there, and this is the first idea. You can just randomly name it. You choose it as you like. Call this one first, call this one second, third, and fourth, right? And then if this is the first one, in the place of first one, in the first entry, you put x, which is sigma x. So essentially, this x, y, z's are nothing but sigma x, sigma y, sigma z, and this thing is I, and the product is essentially a direct product in between them. Okay. So essentially, this one will represent an operator like this, which is x because it's the first one. The first entry is x. The second entry is essentially if it is connected to one of these guys, so it's connected to 2. So because of that, there is a z here, and it is not connected to 3 and 4. That's why there is 2 identity there. So that's the recipe. So using that recipe, you can write down all these operators here, and then the density operator will be an expansion which looks like this. It's natural that you have 4 identities which are direct product, and it's natural that because it's a, it has dimension this. So essentially you normalize it so that the first term ensures that you have probability summing up to 1, and then you have these 4 guys. And then you have the other guys, and it turns out these 4 guys are generator of a group. So this is nothing but the stabilizer group. These are the stabilizers of the state. And if you take product between these 4 guys, you will generate the rest of the guys. Okay. So it's essentially an abelian subgroup of the Pauli group. That's what this is. And this is a very useful structure. So I'm just repeating myself here. So this is the graph. This is its expansion. So looking at the expansion, now what are you looking at? So look at this expansion. You can clearly see that this state is also such that it has no term which has just all identity and only an X and only an Y, which is telling you that this state also doesn't have any magnetization, right? So now if it turns out that it has only, so this term is telling you that it has a quadrupole moment, right? This term is telling you that it's a higher moment when you have 3 of them non-trivial. Like, let me see, do you have such a guy? 3 of non-trivial and 1 I? Maybe not, right? So these are just correlation functions. So what one is telling you is that some specific correlation functions are missing, right? So essentially, what we are looking for when you're looking for these identities, when I say that when you trace out 2 spins and you leave the rest, and it should, when you keep 2 spins and you trace out the rest, and it should be, the reduced density operator should be an identity matrix. What I'm saying is all possible 2-spin correlation functions in the system is absolutely 0. They're not there. Not only that, all magnetization terms are 0, right? And that you can use to your advantage. That's the whole point. Yeah. Yeah, sure.
There is a 2-spin correlation.
No, there is no 1 spin. For this one,
there's no 1 spin, but there are 2-spin correlation.
In this case, that's what I said. This has no magnetization. So I just looking at this expansion, I can tell you what's going on. It's okay. So now let's say, is it easy to prepare these graph states? It turns out, yeah, there are simple recipes to prepare these graph states. And this is a quantum circuit, which essentially creates this graph state. So this is a short form of that. What you have is the Hadamard gate. So what you do is you prepare eigenstates in the Z basis, all up spins, and then using the Hadamard gate, essentially this becomes plus eigenstate of sigma X. And after that, you apply the C0 gate. Here is the table for the C0 gate. This is what it does. And what you get is essentially this graph state. So essentially here, if I want to create this particular graph, all I have to do is use this particular quantum circuit. You can see that if you really have a physical system, imagine that you are using one of these IBM quantum computers. Usually they're kind of linear. And if they're linear, to create a periodic chain is going to be non-trivial because it will correspond to a very non-local interaction. So implementing this is not going to be easy on a quantum computer, which we have now. We need something, the architecture has to be correct really to implement such a thing. So all the nearby gates are all fine, but the first and the last thing to put the periodic boundary condition, that is going to be the problematic one. We'll see how to avoid that. But yeah, so that's the problem. But ideally, you can use quantum circuits to really generate these graph states. Now the question is, how much time do I have? How am I doing in time? Okay, I'm doing okay, fine. So then I continue as long as you allow me to do. So now I think the question we asked is that, so what we call K uniform state is essentially if I give you a large state with a large number of spins, a K uniform state is that state in which if I pick out K spins and trace out the rest, I get identity density matrix, right? That's a K uniform state. So the question we asked is, can we systematically construct 1 uniform state, 2 uniform state, 3 uniform state, 4 uniform state? Is there a recipe? Can you really construct that? And it turns out that sort of figured out actually that this is what fits the bill. So if you need a 1 uniform state, if you take a fully connected graph, it's a 1 uniform state. If you want a 2 uniform state, this actually turns out to be a 2 uniform state. And then these are 3 uniform state. This is a 4 uniform state with periodic boundary condition, and so on and so forth. So we could only go up to here. After that, it was not possible to really construct them systematically. There are 2 questions here, actually. It's a non-trivial thing to figure out what is the smallest size on which it will work. For example, I'm claiming that this is a 2 uniform state, which basically means if you take any 2 spins and trace out the rest, is going to give you an entropy of 2 log 2, or the matrix is essentially an identity 4 cross 4 identity matrix. In principle, you will tell me that you should be given the fact that you are just looking for a 4x4 identity, you should be able to take 4-qubit state and arbitrarily you should be able to figure out a 4-qubit state such that if you trace out 2 of them, you are left with an identity matrix, which is 4x4. Ideally, it should be possible. Mathematically, it doesn't seem like an impossibility. But as far as quantum mechanics is concerned, it turns out, and this is something we confirm, that it does not exist. So there are lower bounds also. If you want the state, how many spins will do the job is a non-trivial question, and it has to be solved for each case individually. There is no general recipe. For this guy, actually, you need 5 guys, and 4 guys will not do the job. Yeah. Yes. Yes, it's also, but this is one of the trivial solutions in the sense, if you take a fully connected graph, it will do the job for you. Okay, but it also gives you a pattern. You see that there is a pattern, at least for the even cases, you see there is a pattern. And this is what will make a condensed matter connection. You see, this is a 1D lattice with periodic boundary condition. This is a 2D square lattice with periodic boundary condition. This is not true for the odd case, but the even case. This is an observation we made in this paper, and that is when our second work started.
Sorry.
Yes.
Just for clarification for the students.
Please.
Are these exactly the same thing as the absolutely maximum entangled states you're talking about? Because you mentioned 4.2. 4.2 is an absolute
maximum. Is maximally, but
yeah.
This one is not.
Right. What I'm saying, no, just I understand, but is the definition of K uniform?
It's K uniform. It's not maximally because
it's not necessary. So you have to choose a subset, and it's only for that bipartition.
Yes.
Okay. So it's not all possible bipartitions of N.
No, it's all possible. It's all possible.
But it's all possible bipartitions that you can have.
The number of qubits to be much larger. That's why I'm asking this question. What is the smallest size in which you can fit this argument? For example, in this case, this is the smallest size in which you can fit in. And n by 2, which is 5 by 2, if you take it as a floor function, it's really 2, right?
Mm-hmm.
5 by 2 is like 2.5, which is you should take 2. So 2 is the answer. Right?
Okay.
But if you go to 6, it's not going to work. So that's right. I think the bound is something like 7 qubits. So beyond 7 qubits, you don't have these EME states.
No, you do have. I mean, for qubits, you mean?
Yeah, for qubits.
For qubits, yeah, sure.
You can have for qubits.
Sure. No, I understand. But yeah. No, my question is, it's the general definition of K uniform is equivalent to absolutely maximum entanglement. So that means that K uniform is not considering all possible bipartition, because AME is for all possible bipartition.
No,
continue.
All possible bipartitioning we are considering, but I think AME has to do with the smallest size to where this will fit the bill. It has to do with the size. What is the smallest size which will do the job?
Add something.
Yeah.
AME is K uniform with K equal to n by 2.
No, it's also about the n.
Yeah, no, it's not.
No, anyway, we can come back to that. Okay. Okay, yeah, that's better. Right? So fine. So now let me go to what is called frustration-free Hamiltonians, and that's the condensed matter connection. So if you have these Hamiltonians, which have the following properties, so it's K local. So essentially, this has support on K fundamental units. So this can be spin half, spin 1, depending on what your system is, but it has support on K guys, K local guys, right? And it is defined as frustration free if the ground state G is a simultaneous ground state of these K locals, right? So HK locals, right? So then you can subdivide into 2 different categories. One being that all these mutually commute, and the other being that they don't mutually commute. And you can see there are some examples here and here. Now, what we could do, we could go back and create a Hamiltonian, which is using the generators which I just showed you, right? And they will be the cluster states. And they will be exactly, they will correspond to frustration-free Hamilton. For example, if I write a Hamiltonian H, which has these terms, which are the generator of the stabilizer group, as the terms in the Hamiltonian with a minus sign in front, then the state will be the unique ground state of that Hamiltonian, which conforms to this criterion of being frustration-free. Which one will be the ground state? This state. This state whose density matrix expansion has these terms.
Sorry, this is for a system with just one plaquette?
One plaquette?
Well, okay, so
in what sense?
Say RK we know the arcane Hamiltonian, all of these, they are infinite systems.
Yeah, here I'm not. See, this is kind of abstract. I'm not. So look at this guy. You won't even talk about any dimension, right? It's a graph.
This was part of the background only. What is it? Sorry.
I think you have a specific picture in mind, probably.
So how finite is your system? What is the size of the system?
In principle, it can be infinite. Infinite with periodic bond.
But I don't understand. So these you have only 4 elements there, as far as I can see.
Here, this one is finite, but I could build state which has this property, with this property, which can be infinitely large.
Okay, so you're writing the terms in the Hamiltonian, essentially, in this fancy.
What I'm trying to say is that this state has this interesting property, which I said is 2 uniform or 3 uniform, but then not this state. So I can write state.
There are the flip terms and the non-flip terms.
Yeah.
Okay. Now I understand.
Okay. So maybe
I was translating to English.
Larger system, then you will have a sum of more terms, and each term will comprise larger
you will have
product, larger number of products.
Interesting thing is that you will have these generators. Okay, my criterion is that the density matrix can be expanded as identity plus an abelian group, such that it has generators which all commute with each other, and the product of them will generate rest of the terms which will appear in the Hamiltonian. And notice there's something very interesting. Each of these operators square up to identity, which means they are dichotomic. Everything is dichotomic here.
But the size of the generator is the size of the system, or the generators remain.
No, it can be larger. You are basically asking, does it need to be 4 generators? No.
Yeah.
No, you can have smaller subgroups. You can have smaller subgroups. It's not a problem. You can ask what is the largest group you can have, but smaller subgroups you can always have.
The more qubits you have, the larger the generator.
But I can always have a smaller subgroup which also conforms to the same structure. You are asking about the largest group. Is that the question?
You want a Hamiltonian. So the larger the number of qubits, the larger terms appear with this.
That's correct. But I'm also telling you that when I construct this Hamiltonian, certain kinds of terms are not allowed. Right? I'm dropping them. So that's the way we constructed the state. That's the condition of K uniformity. But you know that when they appear in the density matrix, I have to make sure that when I trace out n of them, I get the identity matrix, which is telling you certain correlations are simply missing, which means certain terms here are simply missing. These are each correlation function.
So
they're all over the place. Yes, they're all over the place. I agree.
So sure, in the case of the arcane Hamiltonian, in addition to having terms that flip and terms that don't flip, you also have constraints, because you can only have a dimer at one link and no dimers on the surrounding links. Where are the constraints here? So you don't have as many states as you think you do.
Yeah,
it's not 2 to the n.
See here, I'm okay. So let's follow what we are saying. So here, I was talking about the construction of a state which is K uniform. I was heading towards that. And then at some point, I started talking about Hamiltonians. So what I said is that these are interesting states, and now I would like to envision these states as some ground state of certain Hamiltonians. And the question I'm asking is, what is that Hamiltonian?
I can answer.
Okay. The states, essentially, you're going to have these columnar states or the flip states or whatever you want.
Yeah.
But given a dimer here, you cannot have dimer on the other places. So the number of actual dimensions is actually not just 4 to the n or something, it's much smaller.
Can I answer?
Okay, please go ahead.
Yes, there are constraints, and the constraints are additional conditions that you have on the product of these Pauli operators. So you will have things like, for example, products over loops. Okay, for example, in this direction, products over loops over this direction, maybe, products of plaquettes, things like that. Yes, there are constraints.
Okay, but you have not implemented any constraints.
No.
No, so far, no.
No.
He has open boundary conditions. He has open boundary conditions with no constraints. No, I understand about the constraints. I'm just telling, he has no constraints.
I should go and rest for hours.
Yes.
Okay, fine. So maybe we continue this discussion after my talk. Yeah, fine. So you can, so what I'm trying to say is that you can construct this state using quantum circuits, and you can also envision the states as ground states of certain Hamiltonians which are frustration free, right? That's the claim. Now, the observation that, you know, the 2 uniform state and the 4 uniform state happen to be a chain with boundary condition, a square lattice with boundary condition, is not a coincidence. What you could show is the following. So now we come to the statement that the ground state of the frustration-free clusterizing model in D dimension is 2D uniform. So essentially, if you take the clusterizing model, so this is the clusterizing model, this is the clusterizing model in D equals to 1, this is the clusterizing model in D equals to 2, and so on and so forth. So if you take a clusterizing model in D dimension, then its ground state is 2D uniform. It basically means that if you take 2D spins from there and trace out all the other spins in the ground state, no matter how large the system is, the density matrix will turn out to be an identity matrix of this dimension, right? So that's the claim. That's what we prove in our paper. And now these are interesting things, because if you look at the D equals to 1 case, this ground state is essentially a SPT phase with Majorana edge modes. If you look at the next one, it's a ground state of a subsystem SPT. So this is the reference here, but not much is known about D equals to 3, but essentially our proof holds for D equals to anything, right? So it's a general statement. So we don't know what the physical properties of D equals to N is, but what we know for sure is that one common property with the shear is K uniformity. So that's the interesting point. Yeah. How much negative time do I have?
A lot. So
a lot of negative time. Okay. So how much of this negative time should I use? Like 5 to.
I can negotiate 2 minutes.
2 minutes. Okay. So. Okay. So I'm not going to tell you about error correction. Then maybe I tell you. So what was the idea? So maybe I just use the blackboard for 2 minutes. Essentially, what is the idea of the stabilizer codes? The idea is very simple. So what you have is essentially a state which can be, so maybe I go back. Imagine that I have essentially this state, and these are the stabilizers of the state, and squaring, see each of these operators, if I square them, they essentially are identity, which means the eigenvalues are +1 or -1. Each of them is dichotomic, right? So each of them, you can say, bipartitions my total Hilbert space into 2 parts. So you can think of the total Hilbert space of the problem of 4 spins. And if I take any of these stabilizers, then essentially it has ± eigenvalue, +1 and -1. So it bipartitions the Hilbert space in a certain fashion. Then if I take the next stabilizer, then it bipartitions it again. And if I take the next stabilizer, because each of them is ±1, it will bipartition it again, and so on. So essentially, this is kind of partitioning the whole Hilbert space into these eigenvalue sectors, where each of these guys are essentially a sequence of +1, +1, -1, -1, +1. It's telling you what is the eigenvalue of the stabilizer. So if I know the eigenvalue of the stabilizer, I can tell you the state is here. The usual convention is that you take one of these patches which has all the eigenvalues being positive for the stabilizer. So +1, +1, +1, that's usually called the code space. And then the errors in the systems, if I think of single qubit error, they're essentially sigma x, sigma y, sigma z, acting on a particular qubit, right? Let's restrict ourselves for simple errors now, which are only single qubit error acting on a specific qubit. If that is the case, what you could show is that essentially from the code space, it will take you somewhere. But wherever it takes, it essentially corresponds to a very specific sequence of pluses and minuses. So by detecting these pluses and minuses, which basically means because they are mutually commuting, you can make simultaneous measurement of these observables. You can think of them as observables. And once you have these things read out, you can essentially say that this specific error happened, right? This is the whole philosophy of error correction, that you can actually identify error. So what you can show is that if you have a K-uniform state, then you can actually correct and identify K/2 errors exactly. You can not only identify what the error is, you can identify the position of the error. Exactly. And why is this important? This is of extreme importance because if you have to understand what your environment is, imagine that your quantum computer is working in a particular environment. So essentially, you have to understand what your environment is. And if you have to understand that, you have to know where the error happened. It is not enough that you know that there's an error. If you look at all the topological codes, They have ability to correct a very large number of error, but they simply don't tell you, they don't have an ability to tell you what error happened. So without knowing the spectrum of error, it can correct error. That is very good for correction, but as far as benchmarking your environment is concerned, it's a completely different strategy. It's a reverse strategy. You want to know what error happened. And in that case, K-uniformity is a real advantage. We essentially, so I don't have time for it, but I'll just show you the data. We essentially run these programs on this IBM machine for one of the cases. So this is our quantum circuit.
Please leave time for questions.
Yeah.
Yes, sir. As I'm running on negative time, I'm definitely leaving time for questions. So give me a few minutes. I'll be done.
No.
So this is the quantum circuit we run, and so what we get as an output is this. So just to tell you that these are essentially errors which we have figured out using our protocol on the. So let me just. So this is the circuit we run. We are looking at errors which is happening on the middle circuit. Because we cannot put a periodic boundary condition, we leave it open. So essentially, it's a two uniform state, but because we have opened it up, there's no periodic boundary condition here and here. There's some mess here. Just ignore it. So there's some open boundary condition here. Because of this, the two uniformity is destroyed here, but the middle qubit actually enjoys two uniformity, and that's what we kind of implement here in this IBM quantum computer. And what we see is that this is a simulation which we run, right? So, and this is exactly the experiment which we run. And you can see that there's a reasonable correspondence between the experiment and the simulations which we run through this experiment in IBM quantum computer. And the interesting thing is that you see there's a very big difference between the Z error and the X and Y error. And this thing comes from the fact that the initial state, if you remember, the initial input is all up, right? So the initial input is essentially all up state. So it's a
yeah. So wrap up, please.
Okay, fine.
And then we leave for questions. So some students can ask a question. What is a simulation?
I'll just finish and then, yeah. So you have all these ups, and because you have to prepare all these ups, there's a very large error for up preparation. And that's exactly shows up as this gap here. And that's why there is no gap here. And this is consistent with the simulations we run. And with that, I would like to conclude.
Thank you very much.
Apologize very much for the delay.
So now questions. Is a question up there? Yes, please.
I just wanted to comment on K uniform versus absolutely maximally entangled. So if I believe right, you can correct me if I'm wrong, but K uniform means that you trace out up to K systems.
Up to K units, yeah.
Right? So when you do a bipartition, you can pick the dimension of the bipartition. So you trace out up to dimension K, and all such bipartitions up to dimension K will satisfy the maximal reduced subsystem entropy criterion. Whereas with AME, the K has to be
all.
N by 2. If you do N by 2, it's effectively all.
Yes, that's
Because-
the point.
yeah.
So that's what I understood, what I was asking.
Just wanted to
That's okay. Yeah,
Has to do with system size, essentially, yeah.
thanks. Any question? Any other question from the students?
Yes, I have a question. Sourin, are you differentiating between identification and correction?
Yes, I'm differentiating between identification and correction because
So-
if you look at there's codes like Tori codes and so on. So if you look at their uniformity, you will see that Tori code is probably 3 uniform, which basically means it can identify 3 by 2 errors, which is like 1.5, which is basically 1. So as far as identification is concerned, it can identify 1 error. But as far as correction is concerned, it can exponentially large number of errors. So I'm definitely distinguishing between error identification and error correction.
So,
Other question?
general question that comes to my mind, that if you can identify, why can't you correct?
That's absolutely correct. See, the whole philosophy of classical error correction is first identify, then correct. In quantum mechanics, we don't need to do that. And that's an advantage. So I'm saying Tori code has this advantage, but the question is, if you do not identify, then you do not know your environment.
No.
So in our case,
strictly speaking, in quantum, you cannot identify the exact error. That is not possible because your continuous and it is infinitely possible. You discretize the error and then you identify and then
I'm
you correct.
assuming that there's a single qubit error. If I assume that it's a single qubit error and I have 2 uniformity of my state, then the code is capable of identifying absolutely a single qubit error, where it happened, and so on.
Can I just make a comment on this as well? Sorry. Guruda, so error detection is different from error correction, because in error detection, you actually don't identify whether it's an X, Y, or Z error. You just say it is like an erasure, basically. It's as if you just don't know what happened to that qubit. You're just identifying a location. Exactly.
No, here we are claiming more than that. So that's the whole point. I mean, we are saying identification, it's not only the position, I can even tell what happened. So it's like saying that you really identify exactly what happened.
So in your case, you seem to be doing error correction then, is what I would say, from the parlance of quantum error correction. Yeah.
No, because the topological codes exactly do not identify. As I said, Tori code is 3 uniform, so it cannot identify. It can correct exponential number of errors, but it cannot identify errors. So I'm making a very clear distinction here. I do not agree with
the difference here, as far as I understand, is that if you run error correction, you can continue your computation as you correct errors. Here, Sourin and the collaborators, they measure at the end, and only after they got measurement results, they can identify what happened, but that has already destroyed any quantum coherence that was there, because they measured the state.
So in standard error correction also you measure, except you use ancilla to measure. So maybe here they don't use ancilla. Okay.
And they don't have that capability here.
So let me put it this way, the error space, which I'm considering, not just the particular errors, the space of errors, when they act on this state, they leave this state as an eigenstate of the generators, which are the stabilizers, with plus minus sign. And that is why I'm able to identify.
May I suggest, as a chairman, okay,
Quick question.
are you
Absolutely
desperate?
different.
Are you desperate?
No, I can ask it in private.
Okay, good. So let's stop here. Okay, let's thank the speakers again.